Unlocking the Magic of Maxwell Equation, BWE. Myself, Talsane Dutin Reddy, Section CSITA, roll number 22951A, 3326. Introduction. Maxwell equation provide a complete description of electromagnetic phenomena and underpin all modern information and communication technologies. They are named after James Clerk Maxwell, the Scottish physicist whose pioneering work unified the theories of electricity, magnetism, and light. Today, Maxwell equations are the essential tool of electrical engineers used to design all electrical and electronic equipment from cell phones to satellites, television to computers and power stations to washing machines. The theory of electromagnetism was built on the discoveries and advances of many scientists and engineers, but the pivotal contribution was that of Maxwell, who during the second half of the 19th century made the huge conceptual leaps that would enable the great advances in the electrical technologies throughout the 20th century. The four equations. To set the context for the discovery and development of Maxwell equation, it is first important to understand what they are in the modern context. Maxwell's equation refer to a set of four relations that describe the properties and interrelations of electric and magnetic fields. The equations are shown in modern notations in figure. The electric force fields are described by the quantities E, the electric field, and D is equals to E. The electric displacement, the latter including how the electrical charges in a material become polarized in an electrical field. The magnetic force field are described by H, the magnetic field, and B is equals to H, the magnetic flux density, the latter accounting for the magnetization of a material. The emergence of electromagnetism. The sciences of electricity and magnetism and their fusion as electromagnetism evolved through a series of advances from many different scientists. To name all involved won't amount to writing a who's who of 18th and 19th century physics. Here we will concentrate on the contributions most directly related to the development of Maxwell equations. The advances through the 18th century in understanding electric charges and currents, notably the work of Benjamin Franklin and Alessandro Volta, culminated in the work of Charles Coulomb, whose law showed that the strength of electric force varied inversely with the square of the distance to a positive or negative charged object. This law and a similar one of more magnets was later generalized by the work of Poisson and Gauss in the early 19th century, leading to Gauss' law. The physics behind the first of the Maxwell equation. Up to this time, the law of electricity and the law of magnetism were regarded as two separate fields of the physics. This change in September 1820 was Hans Christian Ørsted was setting up a demonstration of for a lecture in he discovered that an electric current can deflect the magnetic needle of a compass. Maxwell theories. By the mid 19th century, the various laws of electricity and magnetism were becoming well understood, and a common theory that could describe all phenomena was sought. Faraday's vision of lines of force pervading space was radical, and the prevailing opinion of his contemporaries was that a theory should instead be based on forces acting at a distance directly from one particular to another. On this basis, Wilhelm Weber developed a theory linking Ampere and Faraday law. However, his theory was flawed as it required a condition that broke the law of energy conservation. Maxwell believed that Faraday was correct, and in the 1850s, as a fellow at the University of Cambridge, set about deriving a mathematical description of Faraday's theory. In the paper on Faraday's lines of force, Maxwell used a fluid analogy to derive his first theory of electromagnetic force field. The fluid analogy was limited in that it could describe only fields around static charges and steady electric currents. Maxwell also formulated mathematics for Faraday's concept of induced currents but could not interpret these within the fluid models. After a period focused on other topics, including color precipitation and the dynamics of Saturn's rings, Maxwell returned to the problem of electromagnetism with a complete new theory. Now, professor of natural philosophy at King's College London, Maxwell published the new theory in four parts between 1861 and 1862 in his landmark work on physical lines of force. Here, Maxwell devised a mechanical model that could account for all known electromagnetic phenomena. His mechanical construction featured spinning cells and ideal wheels that mimic the curling magnetic fields around currents in conductors. This gave successfully to somewhat improbable analogy that could describe Ampere, Faraday, and Gauss law. Indeed, Maxwell was careful to convey end of part of two of on physical lines of force. That is, model was an analogy and not a suggestion of the real mechanism. Subsequent developments. Over the next 2 decades, Maxwell's theory was accepted and advanced by others, notable Oliver Heaviside, Heinrich Hertz, and Henrik Lorentz. Heaviside championed the Faraday-Maxwell approach to electromagnetic and simplified Maxwell's original set of 20 equations to the 4 used today. Importantly, Heaviside rewrote Maxwell equation in a form that involved only electric and magnetic fields. Maxwell's original equations has included both fields and potentials in an analogy to gravity. The field corresponds to the gravitational force pulling an object onto the earth, while the potential corresponds to the shape of the landscape on which it stands. By conferring the equations only in terms of Heaviside simplified them to the so-called duplex notation with the symmetry evident in the equation of figure. He also developed the mathematical discipline of vector calculus with which to apply the equations. Heaviside analyzed the interaction of electromagnetic waves which conductor derived the telegrapher's equation of Kirchhoff from Maxwell theory to describe the propagation of electrical signals along a transmission line. Timeline. 1785 Coulomb's law is published. 1812 Poisson's law is published. 1813 Gauss divergence theorem is discovered. 1820 Oersted discovered that an electric current creates a magnetic field. 1820 Henri Marie Ampere's work found electrodynamics. Biot-Savart law is discovered. 1826 Ampere law is published. 1831 Faraday law is published. 1856 James Clerk Maxwell publishes on Faraday lines of forces. 1861 Maxwell publishes on physical lines of forces. 1865 Maxwell publishes a dynamic theory of the electromagnetic fields. 1873 Maxwell publishes treatise on electricity and magnetism. 1888 Henry Church discovers radio waves. 1940 Albert Einstein popularized the name Maxwell equations. 1966 Ken Yee introduced finite difference time domain method to solve Maxwell equation. Bibliography. Reference of historical significance. James Clerk Maxwell 1856 on Faraday lines of forces. Transaction on the Cambridge Philosophical Society. James Clerk Maxwell 1862 on physical lines of force. Physiology Magnus series. James Clerk 1865 A Dynamic Theory of Electromagnetic Field. Philosophical Transition of the Royal Society. James Clerk Maxwell 1873 A Treatise on Electromagnetism. Oxford Clarendon Press. Oliver Heaviside 1894 Electrical Papers New York and London. Reference for further reading. Martin Goldman and in 83, The Diamond in the Ether, The Story of James Clerk Maxwell, Edinburgh, Paul Harris, Publishing 1983. Basil Manawan, 2004, The Man Who Changed Everything, The Life of James Clerk Maxwell, Chichester Willie, 2004. Paul J. Nahim, 1988, or revisit the life, work, and times of a genuine of the Victorian Age in New York. P. Harman, 2002. The Scientific Letters and Papers of James Clerk Maxwell, Cambridge University Press, 2002. Brucey J. Hunt, 1991. The Maxwellians, Ithaca, Cornell University Press, 1991. About the author. Graham Turnbull is a senior lecturer in physics at the University of St Andrews in Scotland. He graduated with a first class MSc, a degree in physics, and a PhD in physics, both from the University of St Andrews. After postdoctoral work at the University of the Darshan, and he returned to St Andrews as faculty member of the School of Physics and Astronomy. Mr. Turnbull is a senior member of the IEEE, and he has served on the Scottish chapter committee of the IEEE Photonic Society since 2003. In 2009, he led the installation of an IEEE milestone to Maxwell equation. Thank you.